Now we are going to learn the periodic testing of rail and weld using various testing machines in Indian Railway. In this presentation, we are going to learn about the need-based concept behind the periodic USFD testing of rails and welds. What are the frequencies of rail and weld testing? Action to be taken by the USFD machine operator before USFD testing with respect to machine and other preparatory requirements, during USFD testing and after USFD testing. After that, we will understand how to classify various defect patterns observed during USFD testing, and finally what are the action to be taken once the defects has been detected. Let's talk about need-based concept in the periodic USFD testing of rails and welds. This concept is based on inspection frequency versus permissible defect size, service life of rail and the safety, and also defect size versus the reliability of detection of the defect. Optimization of the cost of maintaining of the rails in track will be depending upon the above three parameters. However, other factors like rail metallurgy, loading condition is assumed to be same while analyzing the optimization of the cost. To extract maximum service life of rail while ensuring safety, the inspection frequency should be such that the increase in the defect size can be reliably watched for the longest period without any failure. However, the high frequency of inspection as a general measure is not always practicable as cost of inspection become prohibitive. The cost of maintaining rail can be optimized by relating the frequency of inspection with the number of occurrence. Therefore, the cost of maintaining rail can be optimized by relating the frequency of inspection with the number of occurrence of the defect, that is inspection as and when needed. Therefore, on section where the number of defects occurrence is low, the inspection frequency is also kept low, whereas the section where the number of occurrence of the defect is high, the inspection frequency is also kept high. The inspection frequency and the condemning size of defect are related because chances of missing defects of a small size is high. To ensure higher reliability in need-based criteria of inspection, only two defect categories are kept so as to suitably rise the condemning defect size, and these are related as IMR and OBS. So in rail we are calling them IMR, that is immediate removal, and OBS means kept under observation. And in through testing for the welds encountered, we will say IMRW, so W indicates for weld, and OBSW. And in case of manual testing of the welds, these are classified as DFWO and DFWR, defective weld under observation and defective weld to be removed. Now we will understand the frequency for through rail testing. After the initial USFD testing of rails in the rail manufacturing plant, the subsequent USFD testing need to be carried out at reduced frequency until the rail have undergone 15% of the service life in terms of GMT as given in the following table. For the rails rolled in April 99 or later, the reduced frequency shall be 25% instead of 15% as stipulated earlier. For the broad gauge section, in case of 60 kg rail which is having the assessed GMT as per 72 UTS is 550. In case of 90 UTS, it is 800. In case of 62 kg, in case of 52 kg, for 70 UTS rail it is 300 GMT, and in case of 90 UTS rail it is 525 GMT. Likewise for 90R rail. So from this table we will assess, and accordingly we will carry out the reduced frequency as per the following table. Now we have to look what is the GMT of the root, and if GMT of root is less than 5, then the reduced frequency is 4 years and normal frequency is 2 years. Similarly, if the GMT of the root is 5 to 8, then it is 30 months and 12 months respectively. Accordingly, from this table we will find out and we will fix the frequency of testing of the frequency of through testing of the rails. The frequency of 80 welds is stipulated with respect to the initial acceptance just after the execution as per the 80 weld manual. Then first periodic testing to be done after 1 year or 20 GMT, whichever is earlier, and further test will be based on the root GMT. Like if the root GMT is greater than 80 GMT, then it is 1 year frequency. If it is in between 60 and 80, then it is 1.5 year, and so on. Now let us understand through periodic testing of rails and welds by using machine SRT or DRT, that is single rail tester machine and double rail tester machine. Before starting the testing, the USFD operator must carry out some preliminary checks. These are: the USFD operator must check the condition of battery before start of the work. Only fully charged batteries are to be used during testing. The operator should check proper functioning of control of electronic units. The operator should also check proper condition of trolley and probes. He should also check the junction box, probe cable, contact, water outlet, and also ensure the smooth movement of trolley wheels. Gap between the probing face and the probe shoe should not be more than 0.2 mm, and he should ensure this by feeler gauge. The probe alignment by keeping the rail tester on the rail should be maintained, otherwise there are chances of getting false echo. The machine operator also ensure that instruments are calibrated on weekly basis as per procedure given in para 4.1.1 B of USFD manual. Similarly, the operator also ensure that the equipments has been set for the proper sensitivity as per para 4.1.1 C of the USFD manual. During testing, the USFD operator must ensure that test is conducted as per the specified procedures. This is a trolley which is used for USFD testing. In this trolley movement, we can see if the rail table is having a difference in height, the probe gets stuck up, lifted, and get damaged. Therefore, the alignment of the probe should be ensured, and in such situation, it is better to lift the trolley and move. Therefore, lifting of the machine at the crossing or change in the rail table height at the joints to protect the probe is a must item. The USFD operator must also ensure that adequate supply of water, otherwise the decoupling of probe and rail may take place. This is a screenshot of the LED screen of the DRT machine. Now in this, the operator will feel the necessary input, and after that he will set the machine, and now this machine is ready to capture the echo from the flaws. During testing, the operator should always look for the back wall echo corresponding to the normal probe throughout the testing. This video we can see that the back wall echo for a normal probe reflected from the rail foot for the rail which do not have any flaw. Here we can see that the back echo has occurred at a distance on the horizontal scale somewhere around 8.8 units. Now this scale is set for 200 mm. Therefore, this unit will give approximately and that is the height of the rail. So backwall echo will be visible from the rail foot for a good rail at this point. Now we are seeing the echo from a bolt hole. The location of bolt hole is approximately 80 mm from the rail top. Therefore, the location of echo from a bolt hole is approximately 4 unit on the horizontal scale. Now in this video, we are going to see the flaw echo from the rail head and web junction. The flaw peak is occurring somewhere around 2.2 to 2.4 units, that is around 44 to 50 mm depth from the rail top. This is approximately equal to the location of the rail head and the web junction. Now in case of 70-degree probe, we will not get any backwall echo. So to check for the proper functioning of 70-degree probe, the USFD operator must check the probe bottom with the finger so that he will observe a noise pattern. This type of noise pattern will be observed. Now we can see a flaw pattern that is observed by 70-degree probe. In this video, we can see the screen is frozen for capturing the A scan. Machine is being moved forward and backward at the same location 2 to 3 times to fully capture the flaw. Let us observe this again. Now we can see that as the machine is moving, the flaw echo is getting observed. Now machine is again move in backward direction. You can see the flaw echo is moving in a differently. Now machine will be further moved to ensure that, and in this manner we will able to capture the complete flaw. Now we are seeing the A scan. Now in this A scan we can observe that the typical shape of A scan, I can say, is taking in this manner. Now in this is the maximum height and this is the maximum base width. Whenever we are observing a scan, we are not really interested from which point it originates and from which point it will be ending. We are interested in capturing the difference between the point of origin and point of ending of a echo. That means the bottom of base is the to what extent the echo is moving on the horizontal scale, and secondly we are observing the maximum of the peak. It is not the each individual peak we are going to check, but we are going to check the maximum peak, and with the help of these 2 points the base width and the peak height. It is possible for us to decide what would be the flaw. Now here it has been shown, this is the maximum peak height and this is the base width. Based on these two parameters, we will be deciding the nature of the flaw, or we will classify the flaw. Once the defect has been found out, the operator shall mark at the location of the defect as per the classification. Now what are the action to be taken by operator? After testing, the operator shall maintain proper record of testing, observations, echo pattern and echo amplitude of the defect in a register in a format as per para 5.1.3 or in the TMS as per the procedure is being followed. The details should be supplemented with a scan recorded during the testing. Ultrasonic tester is a delicate instrument, therefore the operator shall take all the possible care during handling, transportation and storage to avoid impact, damage, etc. The operator also carry out the lubrication of the machine periodically and the charge battery after every day's work. Now let us understand how we are going to classify the rail defects. The defects detected during the through USFD testing of rail shall be classified as per Annexure 2A, and whatever welds encountered during through testing shall be classified as per Annexure 2B. The classification of manual testing of welds are separately described in the manual. However, visual defects on the rail weld shall not be clarified by USFD personnel, and the same shall be recorded and brought to the notice of the section PWI for further remedial action. Any sweeping signal on horizontal baseline that does not extend beyond 2.5 division from the left edge of the screen or vice versa shall be recorded as gauge corner cracking and not as OBS. Let us understand the rail defects captured by 4 MHz normal probe. The 0 degree or normal probe is a double crystal probe. It sends longitudinal ultrasonic waves from top of the rail head into the rail and receive back the reflected wave from the rail bottom or from the defect. The area covered by normal probe is shown in this figure. Now we are going to learn about the rail defects captured by 4 MHz normal probe. The 0 degree or normal probe is double crystal probe. It sends longitudinal ultrasonic waves from top of the rail head and receive back the reflected wave from the rail bottom in case of good rail or in case of flawed rail. The area covered by a normal probe is shown in this figure. Here we can see, depending upon the width of the normal probe, which is generally 20 mm, the central portion of the rail head, web and rail foot, approximately 20 mm width, will be captured, top 4 mm being in the noise area or in the shadow zone. So any defect within this area will be captured by this normal probe. In this screen, we can see that the back wall echo of a good rail is at 8.8 unit on the horizontal scale, because the depth of rail section is 176 mm and the horizontal scale is set for this particular case is 200 mm. Therefore, allocation of the back wall echo, which is approximately in this area. Now, sensitivity for this peak is set to be 100%, so that whatever echo from the flaw will be captured, that can be correlated according to the depth. When the normal probe is moved on the rail top along the axis of the rail, the back wall echo do not move on horizontal scale because the depth of rail section is constant. The normal probe can be used to detect longitudinal horizontal defect in the head, web and foot within the area shown in these figures. Like here This is the flawed area on the side view, and then because the depth of the flaw from the rail top is very less, therefore we are getting multiple number of the peaks. Now in that, this one will be the original or the first flaw echo, and subsequently B1, B2, B3, B4 has been described or captured as the multiple of the flaw echo. If the flaw echo generated from the location which is at the rail and web junction, something like this, or here it has been shown in the side view, we will get the first flaw echo and subsequently the multiples. Let us look another type of flaw. If there is a flaw like a hole like this, a piping or along the longitudinal axis of the rail, but the size of the hole is lesser than the web thickness, then we will get the back wall echo from the rail bottom and the flaw echo from the flaw. Here we can see the height of the back wall echo is less because partly it has been reflected by the flaw echo. So depending upon the size of the flaw or the width of the flaw, the energy will be reflected back, and accordingly the amplitude of the flaw echo will be large or small. Similarly, the amplitude of the back wall echo will be small or large. The location of the flaw will be the distance on the horizontal scale will tell at what location this flaw is. Now many times we will not get the flaw echo. The flaw will be oriented in such a manner that it does not get reflected by the normal probe, or it will not be captured by the normal probe. In that case, there will not be any flaw echo pattern. So we need to look from the side probing, or in case where scabs are there in the rail, then also we need to look for the side probing. The principle is same. When the probe is kept on the side face of the rail head, then if there is no flaw, then the echo will be coming from the back of the rail, and then we will get the first back wall, then multiples. Here, because of the flaw, we will get the flaw echo first, and then we will get the multiples. In this case, we can see that the flaw is somewhere in the web of the rail. This case, the flaw size is smaller than the web thickness. In case of bolt hole, we are getting the similar peak, but because the bolt hole is through the web, therefore we are not getting any back wall echo. But if the flaw echo is lesser, much smaller compared to the web thickness, then we are getting the back wall echo, but height will be suppressed, and we are getting the flaw echo also of a smaller height. Only thing what we need to understand here, the distance between the origin and the location of the flaw echo will tell us whether the flaw echo is in the head or in the web or in the foot region. In this case, to ascertain the extent of flaw, we also require to do hand probing using the normal probe as it was being done shown for the rail head. Star crack in the web around a bolt hole can also be detected by the normal probe, but it has certain limitations. Now here we can see as the probe is moving in this direction, we can get the flaw echo. Say here, flaw echo mentioned as a B. This is because of the bolt hole. Now the flaw echo getting at this point has been shown as B1 or B2 depending upon the location. So flaw echo ranging in this direction from one point to other point. So this we will get the B1 and B2 is the shifting flaw echo. Now as the flaw pattern is coming towards the rail head, the depth of the flaw will be reducing from the rail top. Therefore we can see the flaw echo earlier will be on this location, that is B1, and as we are moving away, the flaw echo will be shifting towards the origin, and this will become B2, this will be B1. If the flaw is located in this manner, a smaller flaw that will come within the shadow of the bolt hole. So these cracks will remain undetected with the normal probes. Let us now try to understand what are the classification of defects captured by 4 MHz normal probe during through USFD testing. In this case, the sensitivity of 4 MHz normal probe is set with respect to 100% back wall echo from the rail foot. Now this flaw pattern is first classified with respect to the location of the flaw. If the flaw pattern is observed within the fish plated area, then for any horizontal defect in head, web or foot length equal to the distance between the rail end and the first bolt hole and connected with the rail head, or it could be any horizontal defect connecting both bolt holes, or it could be any defect originating from bolt hole and progressing at an angle towards the head web junction or web foot junction. So depending upon the location of the flaw and depending upon the nature of the flaw, we will observe certain peaks. Now these echo waves or echo peak now condition whether any back echo is observed before or after appearance of bolt hole echo, and that is along with the flaw echo with or without multiples, or drop in the back echo before or after appearance of bolt hole echo. Let us take one example and see. Like this is a oscillograph pattern. Here we are first seeing back wall echo, and as the trolley is moving, we see that suddenly the flaw pattern is missing and we are getting the bolt hole echo, and then again we are getting the back echo from the rail foot. Now this we are getting somewhere around 2 unit, that means around 4 to 5 centimeter below the rail top. That means there is some crack rail head and web junction. So this flaw pattern fall within the fish plated area, and it is like pattern A, any horizontal defect in the rail head or rail head, web or foot junction, and length is in between from the fish plated to the end of the rail head. So here what we are getting, no back echo before or after appearance of bolt hole echo. So this will be classified as IMR. Let us take another example. Here again we are seeing a back wall echo from good rail. Now we are seeing the bolt hole echo, then no echo. So this is after appearance of bolt hole echo, no echo can be seen, and we can see again bolt hole echo appears. It remains for some time, and after that we are seeing the good back wall echo from the rail foot. So in this case we had observed back wall echo from good rail, then bolt hole echo, then no echo at all, then again bolt hole echo, then again echo from good rail. So that will be any horizontal defect connecting both the bolt holes. In this case the pattern no back echo between the bolt hole echo, flaw echo with or without. So in this case we are not getting any flaw echo. So this will be classified as again as IMR. Now let us take the next example. In this case we can see the back wall echo from rail foot of a good rail. Then we are seeing some echo from the rail head area. Then we can see no echo for some time, and then again we are seeing the bolt hole echo. Then we are not seeing any echo for some time, and then we are seeing the back wall echo. And then again we are seeing the bolt hole echo, and then again we are seeing some echo from the rail head. So it gives a general defect where it originates somewhere away from the fish plated area, but it has been carried over within the fish plated area and from bolt hole towards the head at the end of the rail also. So this defect will also be classified at IMR because no back echo before or after appearance of bolt hole echo with or without multiple are seen. Now, if the flaw is located beyond fish plated area, we are still using 4 MHz normal probe. Now, depending upon the location of track or the vulnerability of the track, the IMR or OBS rating will be given. Here, if the track is located in the tunnel or at the tunnel approach within 100 meter, on a major bridge or within 100 meter of the bridge approach, or in the vicinity of a hole near the weld, 50 mm in case of old AT weld and 75 mm in case of new AT weld. So any horizontal flaw can be seen, and that flaw, no back wall echo with or without shifting flaw echo for any horizontal length. So that will be classified as IMR. So let's see this example. Here we are seeing in the beginning back wall echo. Now we are seeing the flaw echo from the head region. Now we do not see any flaw echo, and again we are seeing a back wall echo from the rail foot. So in this case we are not observing any bolt hole echo, or we are not observing from the track whether it is near to fish plated area or near to weld. So depending upon the location of track, this will be classified. If it is at nearby the vulnerable location, then it will be IMR, or if the length of the flaw echo, that we have to physically see what is the length of the flaw echo. For that we have to, the moment back wall echo is not seen, we need to mark on the rail head. We will move further, and then when again we will see the back wall echo from the rail foot, then we will mark it and we will measure that distance. If that distance is more than 20 mm, then it will be IMR, or if it is less than 20 mm, then it will be OBS. And this classification and this observation is to be done when the location of track is not vulnerable. The third category of the flaw that can be observed by normal 4 MHz probe is the vertical longitudinal split or the piping. We have seen a certain schematic sketch. In that case, partial or complete loss of the back wall echo, then side probing shall be carried out with 0 degree probe. If any flaw echo with or without multiple is observed, then that will be classified as IMR. Now we will observe the rail defects. Those are captured by 2 MHz 70 degree probes. The area covered by the angle probe is limited to the railhead area only, and that has been seen in this picture. From the top, from the central probe, we can see the top 20 mm, that will go up to 50 mm, 49 precisely, up to around 49-50 mm at the underside of the railhead, and it will be covering approximately 56 mm depth, leaving 4 mm for the shadow, approximately 52 mm area. So basically it is capturing the head area. When we are combining this central probe with the gauge face and non-gauge face or the field side probes, then the entire head will be captured, leaving roughly 4 mm circumference around the rail surface or around the rail head surface. Now each angle probe are provided in pair. So it will be having a forward looking probe and backward looking probe. Now in this picture, a forward looking probe is shown. That means probe is moving in this direction and the wave is coming like this. It hit the defect and then it gets reflected back and captured by the probe. Now when the probe is away from the defect, the wave has to travel a longer path. As the probe is coming closer to the defect, the wave has covered the shorter path. Therefore, the flaw will originate first farther from the zero or the origin, and then it will end somewhere closer to the origin. And in between, there will be a point where we are able to get the maximum peak. So when we are observing a flaw from angle probe, it will be having a moving peak or moving echo which originate from certain point. In the case of forward looking probe, it will originate at a farther distance from the origin. Then it is moving towards the origin. Initially it will be having a smaller peak, and then the peak will be maximum and then it will reduce back and vanishes finally. Similarly, in case of backward looking probe, the probe is moving in this direction. The moment probe immediately cross the flaw echo, we will get the defect at a very closer location, and as the probe move forward, the flaw echo keep moving away from the origin and finally it will end at the farthest point and then get vanishes. In between, we will get the maximum peak size. In Indian Railway, we are using 3 pairs of angle probes for each rail. Those are 1 pair of central probe. In Indian Railway, we are using 3 pairs of angle probes for each rail. Number 1, central probes, gauge face probes and field side probes. Sensitivity for double line section shall be set with respect to 12 mm diameter standard hole located at 25 mm from the rail top in the rail head, and then this value will be set to the 60%. In this video, we can see a flaw pattern by a 70-degree probe. In this video, we have seen the flaw peak originated away from the origin and then it moves towards the origin as the probe is moved forward. That means it is forward looking probe. In this video, we have seen the flaw peak originates nearby the origin and then it keep moving away from the origin and finally get vanished. That means this flaw is because of backward looking probe. Now, as it is not possible to find out what is the base width or what is the range of movement of the flaw peak and what is the maximum height of the flaw peak at the time of during scanning. Therefore, a scan is to be preserved or the screen is to be brought in the freeze mode and the flaw peaks are to be captured. In this, we can see that the flaw peak appears and it keep on moving towards the origin. Then again the trolley is moved in the reverse direction. Then we can see there is further coverage and the area and the height has been changed. Then again trolley has been moved backward direction. Then again trolley was moved in the other direction and we are able to capture the maximum flaw size. So this type of exercise is being done in the field 2 to 3 times to capture the flaw location with respect to both forward and backward probe so that the maximum range or the extent of movement of the flaw peak and the maximum height is captured. Now this is the maximum height is captured. Now in this A scan, we can see the total base width, that is the extent of movement of the flaw echo, and the maximum peak height. So these 2 points we will carry, we will note down and accordingly we will classify it as the IMR or OBS. Now this is the table annexure 2A. Second classification, this is for 70-degree 2 megahertz central probe and sensitivity is set with respect to 12 mm dia standard hole in rail head, 25 mm from the rail top. This is for non-D marked rail on double or multiple lines. Here also the flaw peak is classified depending upon the location of track. So if the track is located at the vulnerable locations, that is in the tunnel or the approach in the bridge or the bridge approach or nearby the bolt hole of the old AT weld or new AT weld. In that case, the flaw pattern has been shown on the top graph, and if flaw pattern is anywhere away, then it has been shown in the bottom graph. We can see the top graph has been divided into 3 zones and bottom graph is divided into 5 zones, and accordingly it has been shown certain area which is non-reportable, certain areas has been OBS, and certain areas are IMR. So in case of flaw nearby the vulnerable locations, this zone has been shown as IMR and all other are non-reportable. Whereas the track location other than vulnerable, we are having the IMR location is considerably less, whereas the other location including this is, whereas the other location this is OBS, this is OBS, and this location is made as non-reportable. So we will now look at all these points. The next slide. Now here we had divided the graph into 3 zone 1, 2 and zone 3. Zone 1 is bounded on the horizontal scale from 0 to 30%. On vertical scale it is 0 to 100%. Zone 2 is bounded from 30% to 100% on horizontal scale and 0 to 20% on the vertical scale. Whereas the zone 3, which has been classified as IMR, is bounded between horizontal ranging from 30% to 100% and vertical is ranging from 20% to 100%, which is shown as a hashed portion. Now bottom is the A scan captured during USFD testing. Now in this A scan we can see the base width. The base width is shown as 20% and the peak is shown as 70%. Accordingly, we have to choose the location on this above scale, above graph. Now this will be from 20% and 70%, there will be area which is falling under zone 1, and accordingly this defect will be non-reportable. Similarly, in other case, here we can see the maximum height of the A scan of the flaw is around 18% and the base width is around 54%. So this base width and the height, this combination will fall in zone 2 and accordingly this will also be non-reportable. Now let us take another example. Here the peak height is around 40%, whereas the base width is around 43%. A combination of these two will fall in zone 3. So now we are clear how to classify the reportable, non-reportable, IMR or OBS flaws. Let us look. In this case, we are not having any OBS, so that has not been shown here. Now let us take another example. This is the case of location which is not vulnerable. So the graph has been divided into 5 zones like shown here: zone 1, zone 2, zone 3, zone 4 and zone 5. Zone 1 is ranging from 0 to 30% on horizontal scale and 0 to 100% on vertical scale. It is non-reportable. Zone 2 is ranging from 30% to 100% on horizontal scale and 0 to 20% on vertical scale. It is also non-reportable. Zone 3 is ranging from 30 to 50% on horizontal scale and 20 to 100% on vertical scale. This is OBS. And zone 4 is ranging from 50% to 100% on horizontal scale but 20 to 60% on vertical scale, and this is also classified as OBS. Zone 5 is ranging from 50% to 100% on horizontal scale and 60% to 100% on vertical scale. That means the size of the flaw will give a peak which is more than 12 mm flaw and it is covering approximately 50% of the head region. So that has become IMR. Now let us take this example. Here we can see the base width is approximately 2.5 unit and the height is approximately 70%. Accordingly, this 2.5 unit will be somewhere here and this 70% will be somewhere here. So this flaw will lie in zone 1 and it is non-reportable. In this case, we can see the base width is ranging from 1.5 to 6.5, so approximately 50%. So it will be ranging somewhere here, and the height is less than 20%, it is approximately 18%. So this will be somewhere here. So if you will see, this is the location of the flaw on this given graph in the annexure 2, and accordingly it will be non-reportable. Let us take one more example. In this case, the base width is ranging from 1.2 unit to 5.6 unit. So this width is approximately 54%, and the peak is approximately 40 unit. So you can say approximately 40%, and then this will be 54 from here and 40 from here. So somewhere it is falling in zone 4, and it will be reported as OBS. Let us take another example. Here we can see the base width has been increased. It is from 1.2 unit to 7.6 unit. So it is roughly around 64%. Whereas the peak height is somewhere around 45%. So what we can see, 64% is somewhere here and 45% is somewhere here. It will be again falling in zone 4 and again reported as a OBS flaw. Now let us take this defect. Here the base width is ranging from 2.2 unit to 6.4 unit. So roughly the width is 4.2 or say 42%. Whereas the peak height is somewhere around 80%. So if I mark it on, I will say around 42% will be somewhere here and around 80% is somewhere here. So this flaw is again falling in the zone 3, which is, according to this, it will be classified as OBS. Now let us take another example. Here the base width is approximately 1.4 to 7.6 unit. So it is approximately 6.2 or 62%. Whereas the peak height is touching approximately 90% height. So 62% is somewhere here and 92% is somewhere here. So this together will fall in the zone number 5, and accordingly it will be classified as IMR zone. So this defect will be IMR defect. Accordingly we can see any number of, and we can classify depending upon the location in the graph where it will fall. Now the third category of defects which has been listed in annexure 2 is for 70 degree 2 megahertz central probe. Now here sensitivity is set with 12 mm dia standard hood at 25 mm from the rail top, but additional 10 dB gain is given. That means whatever peak we are getting, that normally we are setting at the 60%, but the gain we will increase 10 dB. So the gain was, say, whatever amount, it will be added 10%, and this will be used for single line and demarked rails on double or multiple sections. So this will become single line track or double line track which is having demarked rails. Here again, depending upon the location of the vulnerability, it will be classified as A and B, as we discussed above. This zone, these defects are shown in this diagram on the extreme right hand side, and as per this diagram we can see that the defects are classified. In case of vulnerable location, the defects are classified into two categories, whereas zone 1 is non-reportable. It is ranging from 0 to 20% on vertical scale, whereas on horizontal scale it is having full length anywhere. And second is IMR. there is no OBS. So this IMR is ranging from 20% to 100% on the peak, and for the entire 0% to 100%. Similarly, for non-vulnerable location, the defect has been classified into 3: 0 to 20% on vertical scale and full horizontal scale as non-reportable, then 0 to 50% on horizontal scale and having the peak height from 20% to 100% is OBS, whereas IMR has been classified in this case when the extent of movement or the base width of the flaw echo is 50% to 100% and peak height is ranging from 20% to 100%. Now we shall understand how to classify the flaw pattern for 70-degree probe, whether it is gauge phase or non-gauge phase, and its sensitivity is set with 5 mm flat bottom hole, and that classification is again depending upon the location of the track. If it is in vulnerable location, there is no OBS, and if it is other than vulnerable location, then OBS is also included in that. So accordingly, on the vulnerable location, the graph has been divided into 3 zones. Zone 1 and Zone 2 is for non-reportable. Zone 1 is ranging from 0 to 15% on horizontal scale and up to 100% on vertical scale. Zone 2 is 15% to 100% on horizontal scale and up to 20% on the vertical scale. Whereas Zone 3, which is IMR, it is ranging from 15% to 100% on horizontal scale and 20% to 100% on vertical scale. In case of track located at non-vulnerable location, Zone 1 and Zone 2 are non-reportable. Zone 1 is ranging from 0 to 15% on horizontal scale and 0 to 100% on vertical scale, whereas Zone 2 is ranging from 0 to 20% on vertical scale and 15% to 100% on horizontal scale. Zone 3 and Zone 4 are OBS defects. Zone 3 is ranging from 15% to 30% on horizontal scale and 20% to 100% on vertical scale. Zone 4 is ranging from 30% to 100% on horizontal scale and 20% to 60% on vertical scale. So Zone 3 and Zone 4 is OBS, whereas Zone 5 is IMR defect, and these defects are located in this graph from 30% to 100% on horizontal scale and 60% to 100% on the vertical scale. The flaw pattern will be similar of moving peaks, and we have to take the A scan, and again we will measure the base width of the A scan and the maximum height of the A scan, and accordingly we will find out where these two combination is lying on these graphs, and then according to that we will classify the defect as it has been discussed in detail earlier. Let us now understand uses of 45-degree probes mounted in test rig. The sensitivity of this probe is set to 100% with respect to backwall echo from the opposite side of the rail head. Actually, this test rig is kept on one side of the rail and back echo is received from the other side of the rail, and accordingly it is to be tested. Now in this case we are able to capture the transverse defect in the rail head with the scab or wheel bund on the top surface of the rail. Depending upon the vulnerability of the location on where track is available, this defect is classified. Now when the track is situated on a vulnerable location, then we will get the peak like shown in the adjoining figure, and if this peak is reduced or loss of the signal height is equal to or more than 20% of the full scale height, then this defect will be classified as IMR. When the track is located other than the vulnerable location, in that case, if the loss in the peak height is equal to or more than 80% of the full scale height, then only it will be classified as IMR. Whereas if the loss is up to 20% of the full scale height, then it will be classified as OBS. In case of defects noted on a weld while doing through rail testing, the normal 4 MHz probe with a sensitivity of 100% from with respect to back wall echo, this can able to pick it up any of the horizontal defect progressing at an angle in vertical plane in the rail when the track is situated at vulnerable location or otherwise. Now if the track is situated at vulnerable location and then there is loss in the peak is shown like this, whether there is any back echo or flaw echo like shown in this, then it will be classified as IMRW. And if such a flaw is located at other than vulnerable location, then it will be classified as OBSW. With respect to 70 degree 2 megahertz probes, having sensitivity set with respect to 12 mm dia hole in the railhead, when the track is situated at a vulnerable location, then the transverse defect in the railhead shall be captured and it will be classified either non-reportable or IMRW. If the defect pattern is within this quadrant, then it will be, if the defect pattern is located, shown here is zone 1, which is ranging from 0 to 30% on horizontal scale and 0 to 100% on vertical scale, or in the second quadrant, which has been shown as from 30% to 100% on horizontal scale and 0% to 20% on the vertical scale, then it will be non-reportable defects. If the defect is located in the zone 3, which is shown here, 30% to 100% on horizontal scale and 20% to 100% on vertical scale, then it will be classified as IMR. As shown in the figure below, the A scan is having base width equal to 35% and the maximum peak height is approximately 40%, then this defect will be classified as IMRW. Now, if the defect is located in track other than the vulnerable location, then this defect pattern has been classified into 5 zones. Zone 1 and zone 2 is similar and non-reportable, whereas zone 3 and zone 4 is OBSW and zone 5 is IMR. So, zone 5 is from 50% to 100% on horizontal scale and 60% to 100% on the vertical scale, whereas zone 3 is from 30% to 50% on horizontal scale and 20% to 100% on vertical scale, and zone 4 is from 50% to 100% on horizontal scale and 20% to 60% on vertical scale. Zone 3 and zone 4 is OBSW. In the figure shown below, we can see the A scan is having width equal to 40% and the maximum peak height is equal to 70%, and accordingly this defect will be located in zone 3 and it will be classified as OBSW. Now, in the another A scan pattern, we can see the base width is approximately 60% and the peak height is approximately 50%, and combination of this pattern will be lying in zone 4 and that will be again classified as OBSW. Now, in this A scan, we can see that the base width is approximately 60%, whereas the maximum peak height is approximately 90%, and this combination will yield to a defect equivalent to IMR. So, it will be classified as IMRW. Now, in case of 70 degree 2 megahertz probe, which is suitable for gauge phase or non-gauge phase site, and then sensitivity of this probe is set with respect to 5 mm flat bottom hole. Okay, and with respect to that, transverse defect can be captured in the railhead on the gauge phase or non-gauge phase site, and here also, like previous case, it has been classified for the vulnerable location either non-reportable or IMRW. So, IMRW will be from 15% to 100% on horizontal scale and 20% to 100% on vertical scale. In the A scan given below, we can see that the base width of the A scan is 25%, whereas the maximum peak height is approximately 50%, and this combination will yield to IMRW as shown in the above picture. Now, let us look at the another example. In this, we can see the scale has been divided into 5. Accordingly, zone 1, zone 2 will be non-reportable. Accordingly, zone 1 and zone 2 are non-reportable, and they are ranging from 0 degree to 15% on horizontal scale and 0 degree to 100% on vertical scale for zone 1. For zone 2, 0 degree to 20% on vertical scale and 0 degree to 100% on horizontal scale. So, whereas the defects, those are falling in zone 3 and zone 4 will be OBSW. Zone 3 is ranging from 15% to 30% on horizontal scale and 20% to 100% on vertical scale, whereas zone 4 is ranging from 20% to 60% on vertical scale and 30% to 100% on horizontal scale. The IMR will be classified if it is falling between 30% to 100% on horizontal scale and 60% to 100% on the vertical scale. Let us see one A scan shown below. In that, the base width is approximately 25%, whereas maximum peak height is approximately 30%. This combination will lead to OBSW lying in zone 3. In this picture, the A scan is having the base width approximately 55%, whereas the maximum peak height is approximately 30%, and this combination will lie in zone 4 and it will also be classified as OBSW. Now this combination we can see the base width is approximately 40% and the maximum peak height is approximately 70%. Combination of these features will yield into a defect that will fall into IMRW. Now we will understand what are the actions to be taken after the defect is detected. For example, in case of IMR or IMRW, this is to be defined during through rail testing. This type of defect will be marked with 3 cross with the red paints and it will be marked on the both faces of the web. Interim action is to be taken that SSC or the JEPA USFD shall impose speed restriction of 30 kmph or stricter immediately and to be continued till flawed rail or weld is replaced. He should communicate to the sectional SSC about the flaw location. In turn, the sectional PWI shall ensure that the clamp joggle fish plate is provided within 24 hours. The final action taken in this case should be removal of defected rail or weld by a rail piece not less than 5.5 meter in case of fish plated track or 4 meter in case of welded track, and that is to be done within the 3 days of the detection of the IMR or IMRW. In case of OBS or OBSW, both faces of the web shall be marked with the single cross. As an interim measure, SSC USFD shall advise the sectional SSC within 24 hours about the flaw location, and keyman is to watch during daily patrolling till it is joggled with the fish plate. The final action taken by SSC PWA that it should be clamped with the joggle fish plate within 3 days, and SSC USFD shall specifically record the observation in the location in his register in the subsequent round of the testing. Similarly, the action to be taken after detection of DFWO, that is the flaw in the weld, to be kept under observation. This shall be marked with the red paint a big circle on both faces of the weld in head. The interim action taken by SSC USFD is that he shall impose speed restriction of 30 kmph or stricter immediately and communicate to the sectional SSC about the flaw location. The final action taken by the sectional SSC is that he should protect the defective weld by joggle fish plate using minimum 2 tight clamps immediately with a speed restriction of 30 kmph. This speed restriction can be relaxed to normal after protection of DFWO weld by joggle fish plate with 2 far end tight bolts, one on each side, with chamfering of the hole within 3 days, and joint is to be kept under observation. In case of DFWR, it shall be marked with the double cross in red paint on the weld head. As an interim action, SSC USFD shall impose speed restriction of 30 kmph or stricter immediately and communicate to the sectional SSC about the flaw location. As a final measure, the DFWR weld should be protected by joggle fish plate as explained earlier, and an SR of 30 kmph can be relaxed to normal after providing the joggle fish plate. The DFWR weld shall be replaced within 3 months of the detection. Otherwise, speed restriction of 75 kmph shall be imposed for loaded goods train and 100 kmph for passenger train. As a special note, in case DFWO or DFWR is detected on major bridge or in tunnel or at the approach on 100 meter either side, then the marking shall be done as per previously explained for the DFWO and DFWR. As an interim action, SSC USFD shall impose a speed restriction of 30 kmph or stricter immediately, and it shall be continued till the flawed rail or weld is replaced. He should communicate to sectional PWI about flaw location and who shall ensure that a clamp joggle fish plate is provided within 24 hours. As a final measure, the defective weld shall be replaced within 3 days of the detection. Let us now understand the advancement in the USFD technology, that is B scan. B scan is continuous representation of A scan. In fact, in A scan from the flaw echo, we are capturing the distance of the flaw from the rail surface and what is the peak height. Only these two data we are capturing. Let us say this is the screen on which we are seeing the fly echo. Let us consider a 70-degree probe. From 70-degree probe, if a flaw is there and it is favorably oriented, then the moment flaw will be coming in the range of the 70-degree probe, it will be reflected like this, a small peak. And as the probe is moving towards the flaw, the peak size will be increasing. Then it will be started leaving the flaw and the peak size will be reducing and finally it will be disappearing. So here in this screen we can see there are 1, 2, 3, 4, 5, 6, 7 locations the flaw is captured. Now as we know, the 70-degree probe is useful for capturing the flaw in the rail head. Now let us say this is a representative diagram of the rail. So from here I can say this is the region for the rail head, somewhere this is the region for the web and somewhere this is the region for the rail foot. Now what is happening? Let us say this is a flaw which is oriented, that we are going to capture it. Now when a 70-degree probe is kept here, what we can see, a wave will be started traveling and it will be coming somewhere in this region, and then let us say the bunch of the waves whatever traveling, we can say this position is captured at the 1, and that what we have seen on the previous sketch, that it will be reflected at location 1. Say this is the probe. Now this probe moves little bit, it takes this position, we can say this is the position 2, and from here another wave is traveling and this wave say touches here. Now we will see a little longer, bigger peak, so this will be position 2. It will move little further. Now here another wave will be traveling and say that this is reaching somewhere here, we can say this is the position 3 and so on. Finally the probe will be somewhere here and from there the wave will be out, and then we are seeing no peak and say this is the location 7 as we have seen in the previous sketch. Accordingly, in the A scan all these things will not be visible. What will be visible in A scan is, now let us try it again. So in A scan, position 1 to 7 will be seen in this manner. One dot, this position will be visible like this dot, then adjacent dot, adjacent dot, adjacent dot, and like that we will see from position 1 to position 7. So this will be the way it will be visible in B scan. Now let us go back to the slide. Now here in the slide we can see these are the typical lines which are representing the various flaws. Now depending upon whether it is a flaw or whether it is a feature of the rail, it will be classified as a defect or no defect. Let us see next example. Here we can see a flaw captured by 70-degree probe. This is the region where the flaw is captured. In this screen, this is a typical screen whatever will be seen on the computer monitor. In this typical screen, this is the region which is showing the B scan, and this is the region which is showing the A scan. Now the operator need to corroborate B scan and A scan so that he will able to identify the defect. Now this is a typical defect captured from a 0-degree probe. Here we can see 0-degree probe will be having continuous back echo from the rail foot. So this has been shown here with this green line. It is like this. Now this is the region where it is missing and we are seeing the echo from some other height. Similarly, this is the region where echo is missing. This is the region where echo is again missing. Now this is the enlarged portion. Enlarged portion of this region is shown here. You can see here 156 mm of the portion of the rail foot, or from 156 portion from where there is no echo is seen. That means some defect in the rail pertaining to 0° probe. Now another example we can take for 70° probe. Here we can see this is the typical pattern for the A scan. In this A scan, this is the origin from where the first peak is seen, and this is the end. Now how we will see the B scan? B scan is shown here in this region. There is some line shown here. Lot of dots will be combining together and shown, and this is typically within this railhead section. This we can understand again with this example. Here we can see this is the flaw. When the probe is in this position 1, it will mark this. When it will become in position 2, it will mark this. When it comes in the position 3, it will mark this. When again it comes in position 4, it will mark this. And when again it is coming in position 5, it will mark this. So the entire flaw that has been captured with a series of the dots displaying on the screen. Now again take 170° probe. In this case we can see this is the flaw pattern shown on the computer screen. Again this portion is corresponding to this dots, this portion corresponding to some dot here, and all along we are having the various peaks that has been reflected between the various dots, and again it can be seen that these defects are within the range of the railhead. So this is how we can read the various defect parameters, various defects captured by USFD machine while representing the defects in the B scan graph.